Welcome to Course 2 of Embedded Software Essentials. In these following modules, we will begin to interface our program with architecture-specific software requirements as we begin to code for a microcontroller. In the previous course, we spent a lot of time understanding what the embedded systems development environment is. This included the host environment, the tools, and the platform. The host machine was where we wrote software, compiled object code, and connected to a target embedded system. In order to use this environment effectively, we had a variety of tools such as version control, the compiler toolchain, and the IDE. The embedded platform included a specific CPU architecture and surrounding components like memories and peripherals. Throughout that discussion, we tried to reinforce good software design practices. However, we will now dive deeper into an architecture and learn how to write software that will interface with and support features for a specific embedded platform. It is important as a software engineer that you attempt to develop code to be architecture independent as much as possible. This is because it allows us to have portable and reusable code for other platforms and architectures. Just by using C programming for our embedded applications, it does not mean that we have architecture independent code. It is nearly impossible to write an architecture-independent microcontroller program. In fact, embedded systems really require the software designer to know as much about the architecture and platform as possible. This allows us to optimize our designs, utilize certain features or hardware elements in an application, and create portability between different platforms. We discussed some basic high-level software that has platform dependencies, like the linker file with the program code and program data. The way that a compiler allocates program code and data memory is highly architecture dependent, as there are certain specifications that map the C programming constructs to the physical memory more than just a linker file. How does your code and your data get oriented in memory? How does your code and data get moved between the CPU and the memory interface? These were barely introduced, but they have some serious implications on your program efficiency. There are many more architecture-specific concepts an embedded software engineer needs to know about, more than just this memory interaction and allocation. In addition to the engineer, your compiler must adhere to these same specifications in order to compile and install a statically linked executable into a platform. These specifications are referred to as an application binary interface, or in the case of an embedded system, an embedded application binary interface, or EABI. An EABI is the specification that will provide us the details on the interoperability of our program with other statically linked programs and the underlying architecture. Let us highlight some of the basic EABI specifications you might read about. First and foremost, the EABI will specify information on how your program must be compiled. The translation of high-level to low-level language has specific requirements on things like register use and word size. The word size is the operand size the instruction set architecture was defined around. All operations are written to perform actions on data of this size most optimally. There are specifications on how program code and data are physically sized and placed into memory. The C programming language does provide us with data types, but unfortunately these are not necessarily portable. Some data types have varying size, and a compiler may even implement these types as different sizes optimized for its architecture. The C standard types are actually not the standard way developers declare data, as they can be ambiguous. Even further, allocated information will be aligned within specific boundaries with memory. There are also addressing modes that tell you how your program operates on memory. This specifies information like how your program reads and writes program data. The assembly instructions need to know where that data is and the best way to access it. In addition, the compiled segments that we discussed regarding a linker file and the outputs of building are also specified in an ABI. The calling conventions we discussed briefly with the stack memory segment are specified in the ABI as well. This gives details on how routines are called and returned from. It will provide responsibilities on what needs to be saved or restored by the calling routine and what needs to be done by the routine being called. This process is directly related to the implementations of the stack and the CPU registers. Finally, the ABI will also specify which libraries or helper software functions that perform more difficult software algorithms that you can write in C but not necessarily are supported by an architecture. Hardware without floating point support must implement all floating point math with software routines. If there are existing statically linked libraries, like the C standard library, this will also specify how executables need to interact with the standard library. All of these examples were just basic introductions into some architecture requirements that the compiler handles behind the scenes. Developers need to know these too, as some serious bugs can be introduced without understanding how your hardware will implement your C program code on your platform. The first module of this course will give you your first steps into writing C programs that are optimized for an architecture. By knowing the details of how memory is managed, how to define portable and explicit data, and how to interface with peripheral memory to configure our microcontroller, we will be nearly ready to start writing an embedded application.